Hello everyone and welcome back to Lesson 3, Neural Networks. In this video, we're going to talk about another subcategory in this field known as graph neural networks. So let's get right into it. Now, when we think of graphs, what comes to mind? You might imagine something like this, like a pie chart or bar graph. But when we are talking about graphs in the context of computer science, we're talking about diagrams that consist of nodes and edges. And there are also some different types. So in these sketches here, you can see that the black circles are the nodes and the blue lines in between are the edges. And so first we have directed graphs. So in directed graphs, the edges connecting the nodes have an arrow indicating a certain sense of direction. And an example of this is a food web. So let's say in a food web you have a snake and a mouse that are connected because the snake eats the mouse. That direction is really important, and it can't go the other way around as the mouse eating the snake. So that's why we might need to indicate direction. And then we have undirected graphs where you don't need to have a sense of direction, and the bond exists both ways. So an example here are molecules, because when two atoms are bonded in a molecule, there is no direction, right? The bond is equal for both of them. Then we have weighted graphs. So weighted graphs have a number called a weight that matches up with each edge. And an example of this are maps. So with maps, right, we might not have the actual numbers written on the roads indicated in the map, but right, you're going to have some sense of scale, and the roads are going to be drawn to scale based on how long or short they are. And that, in a sense, is a weight, right? Because a road that is 5 miles is very different from a road that is 50 miles on a map, and it's important to make that distinction. And so here in this sketch, right, we just have a bunch of numbers on each of the edges. And finally, we have unweighted graphs where the weight in between the connections doesn't matter. And one example of this is the internet, right? The internet is sort of like a complex graph in itself. Though there are so many sites, and it would be really, really difficult to create a visual representation of what the internet actually looks like, right? You can imagine it in the sense of links, right? And links will connect different pages to each other. So the pages are nodes, and the links between the pages are the edges. And there's actually a really cool site talking about 6 degrees of separation, which is a graph theory principle, basically saying that any web page on the internet is only 6 links away at maximum. And you can check out the site actually in our video description and on our website if you're interested to learn more about it. And you can check it out where there's a software that finds the closest path between 2 Wikipedia pages. So again, this just shows how graphs are so integrated in our ideas of technology and computer science and neural networks. And another important thing to note is that direction and weight are separate. So just because a graph is undirected doesn't mean it also has to be unweighted. So for example, the World Wide Web is a directed and unweighted graph, right? We talked about how it's unweighted, but it's also directed because a link is going to be on one page and it takes you to another, so it has a sense of direction. And then for example, maps, right? We talked about how maps are weighted, but at the same time, maps are also undirected because you can go on a road technically both ways, right? And we don't put arrows on our roads when we draw maps. And it just depends on which point you're starting at and which point you're going to. So you don't need to pick from just one of these 4 categories. And also there's many more types of graphs. These are just a few. And so to see if you've absorbed this concept, I'm going to give you a question and you're going to try to figure out what kind of graph it is. So let's say a social network. What kind of graph would this be? If you would like, go ahead and pause the video and take a couple seconds to work it out. Okay, so a social network would probably be an undirected graph, since when we think about relationships, right, they hopefully go both ways, not just in one specific direction, right? It's an equal bond between 2 people. And then social networks, you can demonstrate them as an unweighted graph, right? Just filling in people for each of the nodes. But you can also make it weighted by adding numbers to the connections to indicate how close each relationship is or how correlated people are. So I hope that this helped you to better understand what a graph is in this context and the different types. So now let's go ahead and check out how graph neural networks play a role in this. So the first important question we need to ask ourselves is, how do we make graph structured data processable by neural networks? And the answer is the same as in the last video, by converting them into matrices. So we can convert the information stored in each node into a matrix. And we can also represent information about each edge in a matrix. So we would want to include the endpoints of each connection, as well as the weight or direction of the connection if it has one. And finally, we can represent the shape of the graph in a matrix by showing which nodes are and aren't connected. So even though the computer doesn't see the graph all drawn out, it gets an idea of how connected certain nodes are to others. And now, how does the GNN interpret this? So GNNs receive the formatted graph input in the form of matrices, and it outputs a vector of numerical data called a graph embedding. So if you think back to our video on natural language processing, which you should totally check out, it's lesson 2, video 1 if you haven't watched it already, then you'll remember how we discussed word embeddings and how we represented how relevant certain words are to others in the form of a vector. So we can sort of do the same thing with graphs and node connections. So GNNs create graph embeddings by first combining the features of each node with its neighboring nodes like so. So here we have a neural network with 6 different nodes, A through F. And then we're going to try to create a graph embedding representing how connected C is to others. So we're going to represent a connection with a 1, and if it's not connected, it's going to be 0. So of course, C itself is 0 because C can't connect to C itself. And then we also notice that C is connected to A, D, and E. So those get 1s. And C is not connected to B or F, so those get 0s. And this embedding process is going to be repeated in each layer of the GNN. And the output layer finally combines all of this data to produce the final embedding. And this embedding represents the node's data as well as its knowledge of the other nodes in a vector. So now we can compare how CNNs and GNNs are similar and different. So the actual process is pretty similar to how CNNs work, right? We're converting your data into a matrix, and then we're going to pass it through several layers of nodes or neurons. And these two methods can also be combined with graph convolutional networks, or GCNs. And it's important to note that the main difference between GNNs and CNNs is that GNNs are built for generalized graphs. So it can have any number of connections and nodes, and it can have various web-like shapes like we saw in previous examples. But CNNs are best for regularly structured data, like images, because you can represent them in just one matrix of pixels. And GNNs can be created like any other neural network, using fully connected layers, pooling layers, etc. And the type and number of layers depends on the intended output. So for example, you might want to classify nodes. And an example of this is when you build a GNN to analyze the activity of certain accounts on social media and try to predict whether they are a bot or an actual human. Then we also have predicting edges, or basically predicting the type of connections that we may want to make in the future. And an example of this is using a GNN to analyze who else you should add to your friends list on social media. And this is how social media platforms like Instagram and Facebook recommend other people that you should follow based on your current following. And finally, we have clustering. So clustering includes analyzing people's activities and different communities of like-minded people to then target marketing ads based on their interests. And also, here are some other very useful applications for GNNs. And it's important to note that all of this data that we're talking about with the GNNs can be represented as a graph like we discussed earlier. So for example, discovering and analyzing new molecules to use as drugs for treating certain conditions, creating user recommendations based on previously used links, finding the closest path to a location and giving directions, and processing knowledge graphs that label connections between events, locations, concepts, people, or other entities. And again, things like these molecules or a social network of user recommendations or the closest path on a map can all be represented as a graph. All right, I know we learned a lot of new things in this video, so let's go ahead and wrap it all up. So remember that graphs are made up of nodes and edges, and these edges can have weights or directions. So the weights in edges can represent things like the correlation between two nodes, or distance, or something else. And the direction represents the relationship that two nodes have with each other. And it's also important to remember that weight and direction are two different things. So a graph can have weight and direction, or it may have just one, or it may have neither. Also, GNNs use several layers to create graph embeddings, which are vectors representing the analysis, and their overall purpose is to process graphical data. And finally, GNNs and CNNs can be combined to form GCNs. Okay, so I think that's all for today's video. Thank you so much for watching. I hope that you enjoyed learning about neural networks with me. And next up, you can check out Lesson 4, Video 1 on privacy and data security. So I will see you there. Bye!